Okay. Yeah, I'll wait for 2 minutes for everyone to join, and then we shall start the lecture. Okay, so this could be our final lecture in the case of SVM, because today we'll be finishing our discussion with the soft margin SVM, and we'll start the topic of SVM kernels, and we'll get a brief idea that what SVM kernels are doing and how they are helping in the case of non-linearly separable data, right? And on next Wednesday, we'll be getting a brief idea about maybe some of the remaining topics in SVM, if there is, and that would be the end of machine learning section from my side. Fine. So let us start with today's lecture. So before that, let us get a brief idea about what we have discussed so far in the case of soft margin SVM. So I suppose that everyone is clear with the basic idea, basic theoretical concept of what soft margin is doing and what hard margin is, right? So in the case of hard margin, if you recall, what was the point was, in the case of hard margin, we were not allowing any misclassification error. And so there are no points. Suppose this is the decision plane, this is the hyperplane which divides our data, the negative and positive data. So no points from the positive hyperplane were allowed to be inside the margin or on the other side of the margin, and no negative points were allowed inside the margin or on the other side of the hyperplane, that is on the negative side. So this was the case in the hard margin. But suppose we are allowing, in this case, suppose we are allowing certain misclassification to happen. So in general theory, whenever we are implementing it on a data set that is present with us, there is a normal data set that is present with us, it is possible that some of the points may be misclassified. Okay, so in this case, there is a possibility of overfitting. There is a possibility of overfitting, and if there is certain errors, then this constraint, the constraint that we have in the case of hard margin, that is yi into wi transpose xi plus b is greater than equals to 1, will not be satisfied, and we cannot solve this optimization problem. That is a soft margin SVM with this optimization, with this constraint, and with this optimization problem, right? That was our problem. So in order to solve this, we created another optimization problem in order to solve the soft margin SVM. So if you recall, in the case of soft margin SVM, what was the case is, for example, this is the data set that is present to us, and this is the hyperplane. This is the hyperplane which separates our data. Okay, this is the hyperplane which separates our data. Suppose these are the positive point, these are the negative points, and these are the positive points. Okay, just consider these are the positive points. Then it is possible that some of the positive points may be present inside the margin, or some of the, let us take different color. Okay. So these are the positive points and these are the negative points. Then it is possible that some of the positive points may be present inside the margin or may be present on the opposite side. That is, it is possible that some of the points may be misclassified. And in that case, it is not possible to draw a linear hyperplane which separates this non-linearly separable data. So in that case, we have to allow certain misclassification to happen. So we'll be adding one more parameter in this, which is zeta parameter, that is error. Or you can also say this is a penalty that we are calculating. That penalty means what? For example, the distance of this particular positive points from the hyperplane, from the positive hyperplane, that is zeta. Similarly, if there is a positive point present over here, then distance of this positive point from the positive hyperplane will be also zeta. Similarly, if there is a negative point which is present on the positive side of the hyperplane, that will be your zeta measurement, that is penalty that will be added. And we'll be creating an optimization problem such that we'll be trying to penalize this penalty value. That is, we'll be trying to reduce this penalty value as much as possible whenever we are creating our soft margin SVM. So everyone is clear with this basic idea? Yes or no? Is everyone clear with this? Okay. So now let us go through the optimization problem of the soft margin SVM. So in this general case, what we are trying to do is minimize. We are trying to minimize. So if you recall, in the case of hard margin SVM, we had created only minimization of this particular parameter. But in this case, we'll be having minimized this as well as minimize the sum of all the slack value or the penalty value that is present in our data set. That is the slack value we are trying to reduce along with C. C is an hyperparameter, or you can also call this hyperparameter as the regularization parameter, which we had in the case of linear regression. If you recall, we had a regularization parameter, which we had cases. For example, if the regularization parameter is too high, then it is possible. What was the case? If the regularization parameter was too high and regularization parameter was too low, what were the two cases in the case of linear regression? Anybody recalls? What happened in case where regularization parameter was too high and regularization parameter was too low? Okay, in which case overfitting would happen? Low or high? High, okay. Whenever lambda is very high, there is possibility of overfitting. Is that correct? Yes, and if lambda is too low, then it will case underfitting. That is the case? Are you sure about this? Okay. Anybody else? Okay, lambda value is too high, then underfitting, and otherwise overfitting. If lambda is 0, then what will happen? Lambda is 0, then overfitting case is already going to happen. But if lambda is very high, then we'll try to, what will we try to do? If lambda value is very high, we'll try to penalize the value as small as possible. Then in that case, underfitting will happen. Yes or no? Yes, everyone recalls this? Okay. So similarly, in this case also, we have C as a regularization parameter, where C is going to impact. What are we trying to do here is we are trying to reduce our classification error with a trade-off. Classification error with a trade-off with our with the trade-off of our margin. Okay, we want to what do we want to do? Maximize the margin, keeping in context that we want to ensure that some classification error is happening, but we also want to ensure that the margin is as maximum as possible. But in case the for example, if the value of C is very high, then let us see just one diagram that I had pasted over here. Just a minute. Okay, C. So for example, C is very low, then it is possible. If the C value is very low, then that is the possibility that we are trying to maximize the margin. We are trying to reduce the margin maximization problem. That is, we are trying to reduce the W square by 2. Okay, we are trying to minimize this actually, and that value, the slack value, will not have much impact on this. That's why this margin value is higher. But in this case, if the C value is very high, then the classification error, reducing the classification error, is our primary goal at this point of time. Then it is possible that the margin may be low in comparison to what we have obtained in this case. Are you getting the point here? Are you able to see what the diagram is trying to say? Yes or no? Okay, so now let us go through the Lagrange multiplier case of this, and after that we'll, okay. Okay, so our optimization problem. Okay, Okay, so but for soft margin where we are going to consider some misclassification, our constraint will also change where we have a zeta parameter, which is your which is your slack parameter, okay, which is your slack parameter, or you can also call this as a penalty or something like that. So this slack parameter is supposed to be greater than equals to 0, and your constraint will get updated accordingly. That is yi into w transpose xi plus b must be greater than equals to 1 minus zeta I. That is, some slack value needs to be reduced from the actual values that you are getting. Then it is possible that slack value will be greater than equals to 0. If the value is between the margins, if the point is between the margin, then slack value will be less than 1. And if the point is beyond the margin, then the slack value will be greater than 1. I suppose you are able to picture why it will be so, right? So here we have, in the geometric intuition that we had studied so far, we had considered that this value, W transpose xi plus b is equals to 1, and W transpose x plus b is equals to minus 1. So this distance is approximately 1, right? So in this case, if the slack value, if the point is inside the margin, then the value of slack will be less than 1. Okay, so that's why the slack value will be less than 1 whenever the point is inside the margin, and whenever the point is beyond the margin, that is slack value will be greater than 1, then it will be a case of misclassification. It won't be, in the case of slack value is less than 1, it won't be a case of misclassification. But whenever the slack or the penalty value is greater than 1, it will be a case of misclassification, right? I suppose that is clear, right? Okay, so the next thing that we have is now, suppose if this penalty value is equals to 0, then there is no error. And suppose if zeta value is greater than 0, but it is less than 1, then it is a margin error. That is, your point is inside the margin. Positive point is inside the positive margin, negative point is inside the negative margin. And in the case of zeta value is greater than 1, there will be a misclassification error. That is, your point is beyond the margin. That is positive, maybe the positive point is beyond the positive margin and negative point is beyond the negative margin, right? So in this case, signs won't be changing. That is, yi will be having the same sign as W transpose xi plus b. But in this case, the signs will be changing. For example, yi may be minus 1, but your W transpose xi plus b may be positive value, right? Misclassification. If you remember, in the case of hard margin constraint, we had seen that your yi and this W transpose xi plus b will be always of the similar sign. And then and only then you will get a value greater than equals to 1. Okay, up to this, everyone is clear? Yes or no? Is anybody having any doubt? Okay, so now I suppose everyone is clear up to this. So now our optimization problem will change as such. So this is our new optimization problem that we'll be solving in the case of soft margin SVM, wherein our optimization problem f of x, f of w, let us say f of w, will be W transpose w. W square by 2 can also be seen as W transpose W. Whenever we are showing this in the vector form means your W will be in the vector form. Whenever X will not be having 2 or 3 features, it will be having a vector of, it will be in the vector form in your data set that you have present, that is present with you, right? So this, whenever we are doing a vector to vector multiplication, W into W, there will be W transpose W. Yes or no? Are you getting this? Matrix multiplication that am I talking about here, right? So it will be in the form of W transpose W, or you can also say W, here you can say W square by 2 is also okay. Okay, nothing changes in this case, right? Plus C into sum over all the slack values that we have in our data, in the data set that we have. So such that this constraint needs to be satisfied, such that zeta I must be greater than equals to 0, and this value 1 minus this yi into W transpose xi plus b must be greater than equals to 1 minus zeta I. And it also has to follow the KKT conditions that are given to you. What are the KKT conditions that will be derived in this case? Following are the KKT conditions. First is, with respect to all the constraint, partial derivative with respect to all the constraints that are present in your optimization problem will be equals to 0. So here we have 3 constraints, W, B, and zeta. We have to reduce W also, we have to reduce zeta also, right? This, both the things we have to reduce. That's why the partial derivative with all the constraint will be equals to 0. alpha I into G of W will be equals to 0. We have two constraints here. G of W, one constraint is this constraint, that is yi into W transpose xi plus B is greater than equals to 1 minus zeta I. And another constraint is zeta I must be greater than equals to 0. These are the two constraints that we have. Let us say this is G of W, let us say this is H of W. Okay, just naming them with different values. Okay, so we have to say that if you recall, this was one of the constraints that we had discussed. This alpha into G of W must be equals to 0, and at a time only one of them can be equals to 0. So if you recall, in this case we had discussed that support vectors, for support vectors the alpha value will not be equals to 0, right? Similarly, beta into zeta will be equals to 0. Beta is another Lagrange multiplier that we are taking. So if you recall, what will be the actual Lagrange multiplier representation if you represent this particular optimization problem in the form of a Lagrangian function, then it will be equals to f of W plus alpha into G of W plus beta into H of W. Okay, so here since we have two constraints, then two different Lagrange multipliers will be used for each of these constraints. Okay, I suppose that is clear to everyone. Yes or no? Representation in Lagrangian form. Okay. Okay, so alpha into G of W will be equals to 0. Similarly, beta into zeta I will be equals to 0. Both the Lagrange multiplier must be greater than equals to 1. And we had also discussed that G of W and H of W, whatever your constraint are, must be less than equals to 0. So we have to convert this in the form such that it is less than equals to 0. So whenever we create a Lagrange multiplier for this case, it will be something like this. Let us see. L is equals to 1 half W square plus C into Z, summation over I is equals to 1 to M zeta I minus, or you can say plus also, plus alpha I, let us say, summation over I is equals to 1 to N alpha I into, so your yi into W transpose xi plus B must be greater than equals to 1 minus zeta I. So yi into W transpose xi plus B must be minus 1 plus zeta I must be greater than equals to 0. So if you want to convert it less than equals to 0, then apply minus over both the sign, then the inequality will change. So you can say this will be minus yi into W transpose xi plus B minus 1 minus plus zeta I, minus summation over I is equals to 1 to N beta I into zeta I. Okay, this will be a Lagrangian form because zeta I is must be greater than equals to 0 is a constraint that we have, but we have to convert this constraint in less than equals to form. So minus zeta I will be less than equals to 0. Is this Lagrangian form is clear to everyone? Okay. So I would like you to, I'll give you 2 minutes to solve this partial derivative form. That is, you have to convert, get the partial derivative with respect to del L by del W, del L by del B, and del L by del zeta. Okay, these three values you have to get. I suppose del L by del W and del L by del B, both these values will be similar to what we had calculated previously. Only that you have to calculate is del L by del zeta. Okay? Yes or no? So can you calculate del L by del zeta and give me what is the result that you are getting? So I'm giving you 2 minutes. Del L by del zeta. Get me del L by del zeta. What will be the value? Can you tell me what will be the value? So del L by del W will be equals to what we had obtained previously, because here the parameters are similar, right? Even del L by del B will be also similar to what we had obtained previously. I'll leave that to you to solve, but get me what is del L by del zeta. Okay. See, Priyank, we had discussed in the previous lecture also that why are we calculating this Lagrangian? Okay, yes, I'll show the L. And meanwhile, Priyank, I'll answer your question. So, in the case whenever we are trying to solve this SVM, that SVM problem that we have in hand is that we have to calculate, we have to maximize the margin. We had calculated the equation of a margin, an algebraic form of margin, where we had to maximize the margin that was given to us given certain constraints. Now, in previously when we were solving for linear regression and logistic regression, we just had to minimize the loss function that we had in hand, but we were not given any constraints that we had to satisfy in order to solve that particular minimization problem. But here we are given this minimization problem, the maximization problem, with respect to some constraint that we have to follow in order for it to solve. So whenever we have a constraint optimization problem, one way is to convert the constraint optimization problem into unconstrained form, or we can solve this constraint optimization problem using Lagrangian function. So Lagrangian is a method in which through which you will be solving, you will be able to solve this constraint optimization problem. That's why we are converting our optimization problem that is given to us, that is minimizing W square by 2 plus alpha into plus summation over all the zeta I, that is the slack values. Given the constraint, given these two constraints, that is one constraint that we have to follow is W transpose xi plus b is greater than or equals to 1 minus zeta I, and another constraint is zeta I must be greater than or equals to 0. Given these two constraints, we have to minimize the value of W and minimize the value of zeta that is given to us, right? So that's why we are converting the whole thing into Lagrangian form so that we can find way to solve this. And meanwhile, while we are converting, this is a primal form. Primal form and dual form, we had also discussed that primal form we'll be trying to find the values of W to minimize the equation, but in dual form we'll be trying to find the values of alpha to maximize the value, so that finding the value of alpha will be much easier than finding the value of W and B. Is it getting clear now, or still there is some doubt? Are you getting the point? Am I able to? Did I solve your doubt? Whatever your question was, right? So that is why we are switching to Lagrangian equation to solve this particular optimization problem, right? Okay. Can you clearly? Okay. Yes. Just a minute. See, L is equals to 1/2 W square plus C, or summation over I is equals to 1 to n zeta I minus summation over I is equals to 1 to n alpha I into W I y I W transpose xi plus b minus 1 plus zeta I minus summation over I is equals to 1 to m beta I into zeta I. Okay. Okay. C minus sum minus alpha. Okay. That is what you're getting, Prince. Gopal, you have raised your hands. Do you have a question? Okay. Yes, Prince is getting this value, that C minus sum over alpha I minus sum over beta I is equals to 0. So this is the value that you are getting. You can say that alpha plus beta is equals to C. Something like this? Yes or no? Yes? Okay. So now, shall I go proceed? So are others solving, or shall I proceed with this? Okay. So if you see, we can say that upon solving, we are getting this alpha plus beta is equals to C. That is what we are getting. So the only change that we'll be getting in the case of soft margin in comparison to hard margin is we'll be having an upper bound to the alpha, bound to alpha values. So now if you can say that alpha plus beta is equals to C, then you can represent beta in C minus alpha. You need not calculate a beta. Okay, you need not calculate beta. The final dual form of equation that you will be getting, the final dual form, if you will so after calculating, so you will be getting certain equation for W, And similar to what we had obtained previously, also we'll get alpha I into yi is equals to 0. That also we had obtained in the case of hard margin. These two values we had obtained in the case of hard margin. And finally, if you substitute, your Lagrangian dual form for this case will be similar to what we had obtained in the case of primal form. In the case of hard margin, that is alpha I alpha j, yi yj, and xi xj. Okay, so we had obtained something like this dual form we had obtained in the case of hard margin. In the case of soft margin also, we'll get a Lagrange equation like this only. I'll leave to you to solve that particular entire equation and get this particular value. So whenever you will solve this, you will get a dual form similar to this, dual form for the case of soft margin similar to this. And we have alpha plus beta equals to c. So if you see, ultimately we have to find a certain value of alpha to maximize this particular value, but we have to maintain certain constraints while doing that. That is, in the case of hard margin, the alpha I was greater than equals to 0. There was no upper bound. But in this case, there will be an upper bound. That is, C alpha must be less than 0, must be greater than 0, but less than C. Okay, since alpha plus beta is equals to C. So alpha is equals to C minus beta. And beta is also supposed to be greater than equals to 0 because beta is a Lagrangian multiplier. So that's why the C alpha value will be within this constraint, 0 less than alpha less than 1. So we have minimizing the misclassification error while maintaining the maximum margin. Given this particular constraint also, we are following this constraint also, where 0 less than alpha less than C must be followed. Are you getting this? So only difference between the hard margin and soft margin after performing this whole calculation will be, ultimately we'll be trying to find out the values of alpha to minimize W, B, and zeta. That is what we'll be doing. But we'll be having certain constraint to alpha. That is certain value. It should be between the C value. And also you have to calculate certain C values. So if you are increasing the C value, then you are trying to minimize the margin, minimize the misclassification error ultimately. So minimizing the misclassification error, what it will lead? It will lead to minimum, the margin distance will reduce ultimately. So if you have less C value, then you are focusing more on maximizing the margin. Are you getting the point? Is everyone clear with this, what I discussed just now? Or is there any doubt? Yes or no? Okay. Okay. Yes, Priyank, what is the doubt? Just tell me. Okay, yes. So, see, Priyank, what I'm trying to say is, whenever you will solve, okay, see, we are optimization problem, we are new optimization problem in hand now, where we are trying to minimize W square by 2 plus sigma zeta I. Just a minute. Okay, so we have new optimization problem in hand where we are trying to minimize W square by 2 plus sigma zeta I, given the two constraint that yi into W transpose xi plus b must be greater than 1 minus zeta I, and zeta I is supposed to be greater than equals to 0. And it also is supposed to follow the KKT condition. So KKT condition says that you have to perform the partial derivative with respect to W, with respect to B, and with respect to zeta. Whatever parameters are present in your optimization problem, with respect to all, you have to perform the partial derivative and equate to 0. And after equating to 0. So in this case, if you recall, in the case of hard margin, we had already performed with respect to W and B. If you perform the same with the new Lagrangian equation that we had obtained, so the new Lagrangian equation, just a minute. So in this case, this is the Lagrangian equation that we'll obtain with this optimization problem and the two constraints that we have in hand. With each constraint, we'll associate a Lagrange multiplier. So we have two constraints. So with first constraint, we are associating alpha as a Lagrangian multiplier. With the second constraint, we are associating beta as a Lagrange multiplier. So with this new L, if you perform del L by del W and del L by del B, then something similar to what we had obtained in the case of hard margin will be obtained here. Now, new one is del L by del zeta. After performing del L by del zeta, you'll get an equation that is alpha plus beta is equals to C. That is what you'll obtain. Alpha plus beta equals to C. Now, if you'll substitute the values of W that you had obtained, which was summation over alpha I, yi, and xi, I suppose, and alpha summation or alpha I by I is equals to 0. If you substitute this in the Lagrangian equation that we have created for this case, the Lagrangian equation that we have created for this case, then you will get a dual form similar to what we had obtained in the case of hard margin. Okay, a dual form which is similar to what we had obtained in the case of hard margin. Now in this case also you have to obtain the value of alpha only. You have to guess the value of alpha only. You have to find new values of alpha to satisfy this equation, but with one constraint, additional constraint, that is 0 less than alpha less than c. That is, alpha must be, the upper bound of alpha must be c. Okay, in the case of hard margin there was no upper bound of alpha. Alpha was supposed to be greater than equals to 0. There was no upper bound. But in this case, the upper bound is supposed to be 0 less than alpha less than c. Okay, that is the only difference that we have in the case of hard margin and soft margin. And also that another constraint that we have, another Lagrange multiplier beta must be greater than equals to 0. Are you getting now? Is it getting clearer now? Or still doubt? I suppose now it is clear, right? Okay, and while C, what is C? C is a regularization parameter that we are choosing in order to create a trade-off between the minimum misclassification error and the margin error. Margin error is W square by 2 and the misclassification error is sigma C, C zeta I is, this is a misclassification error. This is trade-off that we are getting in the case in both the values. So if the C value greater than is much high, then it is possible that we are trying to fit all the data. We are trying to reduce the misclassification error as much as possible. But if C value is low, then we are omitting the misclassification error and we try to calculate a margin anyways, right? That is the main difference that we'll be estimating in the case of a C. So we had seen the graph previously also, right? Now, I suppose up to this everyone is clear. So shall we proceed with the next topic, that is kernel trick in the case of SVM? Shall we proceed with this part? Okay. Okay, so this will also practically implement tomorrow in the lab session also. But kernel trick is one of the many very interesting trick that we have in the case of SVM. So some of the topics you might find it confusing, but it is very it will be easier once you understand what is the idea. So whenever we have a non-linear kind of SVM, one way to solve this is you have to convert this into a higher dimensional form, and then you solve the process by creating a hyperplane to solve this particular problem. So maybe your problem can be something like this. For example, you have a data set something like this, where you have, these are the positive points in your data set and these are the negative points in your data set. Okay, so this is a non-linearly separable data. You cannot create a hyperplane to separate this form of data. Yes or no? You cannot create a hyperplane. One way to solve this is convert this in higher dimension. Convert this in higher dimension means convert all the data points into some higher dimensional space. So for example, now this data set may be converted. Let us see, I'm just considering this in 3 dimension. Okay, I'm not able to draw in 3 dimension here, but let us see, this is X, Y, and Z. Okay, this is a 3-dimensional form of plane. And suppose the data points is separated something like this. X are over here, and suppose all the dots are over here. Whenever you are converting into 3 dimension, if you want to imagine, you may consider that X may be thrown a little upwards, shown a little upwards in the. It will be elaborated a little upwards from the points, from the negative points. So now we can create a plane to separate these 2 points. Are you trying to able to imagine what I'm trying to say here? Are you able to imagine what I'm trying to say here? Okay, so ultimately we'll be able to draw a plane to separate. We'll be able to create a hyperplane to separate these 2 points, separates the positive and negative points. Okay, so one of the points that is important is you have to convert the X, that is original domain value, original domain. That is, your data set will be in the form of X, that is a feature set that you have in hand, will be converted into high dimensional space. Consider a phi. Phi is a function. Phi is a function through which you are converting your X into some higher dimension. Phi may be any function. phi may be function of x square. Let us consider that your new feature set that you are creating is actually x square. Okay, so if your data set was something like this, x was suppose, let us consider x was 1 2 3 4, then your new dimensional was 1 4 9 and 16. Okay, this is a new feature set that you are creating, and now you will be separating, now we will be applying SVM on this new feature set. So what we'll be doing is we'll be converting x to some higher dimensional form using the function phi. Okay, I'm just naming the function as phi. That function phi could be x square, x cube, x1, x2, or anything like that. Okay, any function. Let us consider that this is zi. So in order to solve this problem will be computationally very expensive. How it will be computationally very expensive? So let us see. So if you recall your Lagrangian equation, Lagrangian dual form that you had obtained was summation over alpha I minus 1/2 summation I j, alpha j, yj, xj. Okay, this was in the case of whenever your data is linearly separable. Okay, this was the case whenever your data was linearly separable. If you recall, we had also discussed that your Lagrangian dual form was the product of all the input dimension that you have, input features that you have in hand. It is the product of all the input features. So now, if you are converting your data into higher dimension, okay, higher dimension, if you are converting your data into higher dimension, your W was also equals to summation of alpha I, yi, and xi. This was something there in the case of W also. And your final equation, which is equals to W transpose xi plus B, let us say G is your final equation. And suppose you are finding for a test data xt. Let us say this is a test data xt. Then G is also equals to summation alpha I, yi, xi, xt plus B. Okay, and then based on the value, based on the negative or positive sign, you will be classifying this particular new test data into positive class or negative class. Okay, I suppose that is clear to everyone, right? So this was the Lagrangian that we had obtained in the case of linear separability. This was the W equation that we had obtained, and we had a function to a decision function, which was W transpose xi plus B, where if you add a test data, if you're trying to classify a new test data, your G will be ultimately summation over alpha I xi into xt plus B, and based on this sign, we'll be trying to separate whether it is in positive class or negative class. Okay, this was in the case of normal linear separable data. I suppose that is clear to everyone. Yes? Yes or no? Okay. So now if you are trying to convert, now in this case, just a minute, let me take. Okay, so now if you're trying to convert this xi and xj into some higher dimensional form, okay, this was when you are the data was not in higher dimensional form. Now if you are trying to convert this xi and xj into some higher dimensional form, then ultimately your Lagrangian equation will be summation over alpha I minus 1/2 summation I j, alpha j, yj into phi of xi into phi of xj. Okay, where phi of xi is some higher dimensional form for xi, and phi of xj is some higher dimensional form for xj. Are you getting this? Similarly, W will also be converted into summation over alpha I yi into phi of xi. Similarly, the G is the decision function that we have, will be also converted into summation alpha I yi phi of xi into phi of xt, that is the test data set plus B. And based on this value, you will be estimating whether if it is positive, it will be classified into +1. If it is negative, it will be classified into -1. Okay. So now what is the problem that we are facing over here? If you see, we have to estimate the higher dimensional form for xi also. We have to estimate the higher dimensional form for xj also. In short, we have to estimate the higher dimensional form for all the features that is present. X is suppose 100 dimensional feature, 100 dimensional. X, the original domain that we have, original feature set that we had was suppose 100 dimensional feature set. Now we are converting this 100 dimensional feature set maybe into 10,000 dimensional feature set. In the case of 100 dimensional feature set, we had the product of xi and xj. So we had something like 100 multiplication between xi and xj. But now, if we are converting this into some higher dimensional form, then your products will also increase. That is, your the product amount of product that you are doing will also increase ultimately. Similarly, whenever we have to find the values of g, so whenever we are calculating for some test data, that data also needs to be converted into some higher dimensional and needs to be performed calculation. So ultimately, this will be computationally very expensive. Are you able to see why it will be computationally very expensive? Yes or no? Are you able to see the problem here? Yes. Are everyone able to see the issue that we are trying that will be facing over here? Okay. So now, in order to rescue from this computation, this high order computation that we are facing right now, there comes a problem. There comes a solution called kernel trick. Okay, kernel trick is one of the solution that we have in order to save us from this high order computation in hand. So kernel trick is something like, kernel trick is finding a kernel function in the form of xi and xj, which is equivalent to phi of xi and phi of xj. So it will be a similarity kind of function. Instead of performing this, instead of finding the higher dimensional form for xi, a higher dimensional form for xj, and then performing the product of those higher dimension, that is what is the first problem that we'll face here is we have to save all the features, save all the new features that we have obtained. Okay, are you getting this? Save all the new features. That is, in short, our feature set will increase in a high form instead of. So what will be the problem that we'll be facing? Suppose you are converting into phi xi. You have a xi term which is of 100 dimension, and now we have obtained phi of xi, which is of 10,000 domain, 10,000 dimension. Let us consider it is of 10,000 dimension. That you have converted your xi into some higher dimension to now, in order to perform this multiplication, you need to save this 10,000 features that you have obtained somewhere in your data set. So ultimately, that will be very expensive process for you. But can you? But instead of doing this, instead of learning all the new features that you have obtained, we can instead use a kernel function, which is a similarity function, which will perform, which will be, if you use the kernel function, it will, the operation that it will perform will be similar to this operation. Okay, so we ultimately need not perform this operation, need not learn the new high dimensional function also, just use the kernel function to perform the operation. Instead, kernel function will reduce the amount of operation, the product operation also. Computationally, it will be less costly. The cost of computation, the cost of k xi xj will be similar to the normal product xi xj that we were performing in the case of normal linear separable form. Are you getting the point why we have introduced the kernel function? I'll go to the elaboration of it, but up to this, everyone is clear why what we are going to do with the help of kernel function? Are you getting the clear idea? Getting the picture or not? So ultimately, with the help of kernel function, what we are going to do is try to reduce the complexity. Yes, we are trying to reduce the complexity means we need not learn the new higher dimensional form of data. We need not learn this also. Instead of learning these parameters and performing the computation, which will be very costly for us, we'll create a kernel. We'll use a kernel function instead. The kernel function, the operation performed by kernel function will be similar to this operation. So ultimately, we need not learn the phi xi at all. Are you getting me? We need not learn the phi xi at all to perform the operation. Let us see through an example. Okay, let us see through an example that will be more clear too. So let us say, okay, so let us say my phi xi, phi x is equals to x1. Suppose x is a two-dimensional feature set. Two-dimensional feature set means what? Suppose x is a two-dimensional feature set means x1, x2. Okay, these will be the two features that will be present in the data set. So let us say phi of x is x1 square, root 2 x1, x2, and x2 square. Okay, this is the higher dimensional. So from the two-dimensional, you are converting to three-dimensional form. Okay, this is the phi of x. To convert the data set into higher dimensional form, एक मिनट सर जो आया नहीं वो थोड़ी देर પછી આવશે 10:30 Okay, hello. Am I audible? Okay, yes. So what was I saying? Let us consider this particular example in hand where we are trying to do this. Where we are, what we are doing is we have x, which is of two-dimensional form, which is of x1 and x2. Okay, this is a two-dimensional form, x1 and x2. Now we are going to convert this two-dimensional form into this three-dimensional form using this phi of x, which will be of the form x1 square root 2 x1 x2 and x2 square. Okay, this will be our new three-dimensional form of data. Now let us consider that we have a data set with a and b. Okay, let us say we have a and b. A and b are two instances in our data set. Two instances in our data set. So a will have a1 a2, b will have b1 b2. Similarly, if we convert a into a three-dimensional form, it will be a1 square root 2 a1 a2 and b2 a2 square. Similarly, b is equals to, in the three-dimensional form, will be b2 square root 2 b1, b1 square, b1 b2 and b2 square. Okay, yes or no? A and b are two instances in our feature set. Okay, a and b are two instances in our feature set. So a and b will be in the two-dimensional form, will be represented as a1 a2 and b1 b2, but in three-dimensional form will be represented as follows. Now if we perform the phi of xa and let us say phi of a and phi of b. Let us say we are performing the product of phi of a and phi of b. Okay, let us say we have a as phi of a is our a1 square root 2 a1 a2 and a2 square, and b phi of b is equals to b1 square root 2 b1 b2 and b2 square. Okay, let us say we are performing the product of phi of a phi of b. So it will be equals to a1 square root 2 a1 a2 a2 square into b1 square root 2 b1 b2 b2 square. So now if we want to perform the product, we have to transpose this, right? We have to perform the transpose of this. Yes or no? Whenever we are performing the product of this, we have to transpose this in order to perform the appropriate multiplication. So if you perform the product, you will get something like this. Let us see in the calculation itself. You'll get something like this, which will be of the form a1 square b1 square plus 2 a1 a2 b1 b2 plus a2 square b2 square. Okay, it will be something like this. Ultimately, this is equals to a1 a2 plus b1 b2, a1 b1 plus a2 b2 the whole square. Yes or no? And this is equals to a dot b the whole square. Yes or no? Tell me, are you getting this? Hello? Okay. See, we had a and b, which was of two-dimensional form a1 a2, and we had b, which was two-dimensional form b1 b2. Okay, this was a two-dimensional form from our original feature set. Let us say x is our feature set, and these are the two instances in our feature set a and b, two instances, which is a1 a2 b1 b2. Now we'll convert each of these two-dimensional feature set into three-dimensional form, where we are using this phi of x, this higher dimensional data. So phi of x is our function through which we'll be converting our two-dimensional data into three-dimensional form. The phi of x is actually x1 square root 2 x1 x2 x2 square. So we have converted both a and b into higher dimensional form. A is a1 square root 2 a1 a2 a2 square, and b is b1 square b1 b2 root b1 b2 and b2 square. Now in order to perform in the dual form, if you recall, we had to perform, whenever we are converting into higher dimensional form, we had seen that we have to perform the multiplication of xi xj. We are performing the multiplication of xi and xj in the case of Laplace dual form that we had created. Similarly, also after converting to higher dimensional form, what we'll be doing? Suppose we are maintaining this higher dimensional form. What we'll be doing is we'll be performing the product of phi of A and phi of B. Okay, we'll be performing the product of phi of A and phi of B to obtain the ultimate solution. So suppose the phi of A, the phi of A is A1 square root 2 A1 A2 and B1 square root 2 B1 B2. Now suppose we want to perform the product of this, both have similar dimensions, so we'll perform the transpose of this and to perform the product of both of this. So ultimately the product will be A1 square B1 B1 square A2 A1 A2 B1 B2 plus A2 square B2 square, which is ultimately A1 B1 plus A2 B2 the whole square. Yes or no? Which is ultimately A1 B1 plus A2 B2 the whole square. And A1 and A2 are instances, are the dimension of A, and B1 and B2 are the dimension of B. We can say that it is ultimately the product of A and B. Yes or no? A and B the whole square, A dot B the whole square. Yes or no? Because A is A1 A2 and B is B1 B2. So if you see, instead of yes, product of two vectors, A and B are two vectors that we have, A dot B the whole square ultimately. Instead of finding phi of A and phi of B, I can directly perform the A dot B the whole square. I need not go and find phi of A and phi of B. My kernel function, this value that I am obtaining here, my kernel function will ultimately find the product, while to find the similarity in the terms of my original dimensional form instead of finding the higher dimensional form. So in what is kernel function ultimately doing? So for example, this was the case of polynomial kernel. Polynomial kernel is of the form 1 plus xi xj the whole square. So what is polynomial kernel doing? Instead of learning this higher dimension, for example, the higher dimension is x1 square, x2 square, xi, x1, x2, root 2, x1, x2. These are the higher dimensional form of features. Okay, higher dimensional form of features. Instead of learning these values, what it will do, it will ultimately find a similarity to this product, ultimately find a similarity to phi of x, phi of A and phi of B product using this original feature set that we have, original feature set. So instead of finding the whole thing that we did in this case, instead of finding the phi of A and phi of B and performing the matrix multiplication and then obtaining the value, I can directly do A dot B the whole square and still obtain the same value. So why do we go? So instead, are you getting the point? So it is actually, instead we are not even going to learn the parameters that we have created using phi of x. Instead, what we are going to do, we are going to perform the calculation with respect to our original feature set only. We are not going to learn the parameters that we have created in higher dimension. We are not going to learn those, but using this kernel function, we'll be making our computation much more simpler. That is, our computation will be in the form of the products of our original feature set only. Are you getting the point? Are you getting how it is getting simpler over here? Yes or no? Is everyone getting this? Okay. So ultimately, if anybody is having any doubt, please let me know, because so the main idea. So the main idea behind kernel function is to remove this, to remove the idea, instead of learning this phi of x, will learn our original x features only, will learn those only, and will use appropriate kernel functions to perform the separation in higher dimension. So we'll not learn the new features that are created. We need not save those new features as well. We just have to perform the calculation with the original features in hand by using an appropriate kernel function, which will draw a similarity with this value, with phi of xi and phi of xj. Okay, it will draw a similarity to this product. So instead of actually going into higher dimension and learning those parameters in higher dimension and then performing the multiplication, I'll stay in the lower dimension only, but I'll stay there and I'll do the multiplication with the lower dimensional features only. I need not increase my computational cost by learning all these features in hand. Okay, are you getting the point? Why how the kernel function is reducing the computational cost over here? Yes. Okay, is everyone clear with this? Anybody is having any doubt? So in kernel function, one kernel function that we saw is 1 plus xi xj the whole square. This is a polynomial kernel that we have. Another kernel function we also have is RBF kernel, and we have a sigmoid kernel. Okay, one of the problematic tasks in hand will be to find out appropriate kernel for performing the classification for our non-linearly separable data. Okay, that will be one problem that is hard to solve. But otherwise, after finding an appropriate kernel, you can easily solve this particular problem. That is, you need not go and learn all the features of higher dimension, just perform the computation with the dimensional features that you have in hand, lower dimensional features that you have in hand, and the computation will be much simpler. Right. Tomorrow also in lab, we'll be performing the implementation for SVM kernel based implementation will be performing. So you'll get a better idea that how it is performing the calculation and how it is performing the classification in the case of non-linearly separable data. So ultimately, kernel function is a function going to help with our calculation that we are going to perform, and it will also help us to perform the appropriate classification of data. So here our idea, I think some 2-3 points is remaining in this context, which we'll be discussing in the next lecture. I'll be uploading the PPT for the same today itself. I forgot to upload it previously, but I'll upload it today itself. So go through entire PPT. And tomorrow we'll be discussing the same kernel function based SVM in our lab session also. So be prepared for that also, so that you'll be getting better idea for implementation as well. And after this, in the last one lecture that is remaining for us to discuss, we'll discuss some of the remaining points in the case of SVM and draw some similarities with other classification algorithm. And that will be end of our machine learning problem, right? Machine learning theory. So today's lecture is clear to everyone, yes or no? Okay. Still, if you have any doubt, you can contact me through email, or you can discuss in the next lecture also. So I'll be uploading the PPT. So in the next lecture, be prepared and go through anything that you are having any doubt in the third section with respect to third session, right? So we'll be discussing that. Fine. Keep your repositories updated as well. So your internal marking will be done with the repositories and the lab work that you have done. So keep them updated as well. So I'm ending the meeting now. So we'll meet tomorrow in the lab, right?